Hello all, we are continuing now in chapter 7b. So this next topic in chapter 7b, writing the electron configuration of a neutral atom with s and p electrons only. So in 7b part 1, we looked at phosphorus. It was a neutral atom, so we just looked at the periodic table to see how many electrons it had based on its atomic number. We can do that for all neutral elements. If something is an ion, like a cation or an anion, we either have to remove some electrons or add some electrons to its electron configuration. We will do an example with ions. Here we are sticking with another example with a neutral atom. So for this practice problem, write the electron configuration for a neutral atom of boron. So for boron, that is found right here, has an atomic number of 5. That means it has 5 protons and also 5 electrons. It's neutral, right? So it has to have an even number of protons and electrons. For a review, let's also figure out the number of neutrons. We haven't done that in a while. So its atomic mass is 10.811. We can round this up to 11 AMU just for the sake of figuring out a whole number of neutrons. So we know that is going to be the number of protons plus the number of neutrons, because this reflects the mass, what's in the nucleus, just protons and neutrons. The mass of electrons is essentially negligible, because the mass of electrons is so light compared to the mass of protons and neutrons. So with 11 AMU, there are 5 protons from the atomic number here. So 11 minus 5 must mean this has 6 neutrons. So we're going to need to be comfortable looking at the periodic table, definitely finding out the number of electrons. Don't forget also, though, how to determine the number of protons and neutrons as well from the periodic table. So we can write the electron configuration like we did for phosphorus. First, we want to count the total number of electrons in the atom. We need to do this carefully, depending on if it's a neutral atom or an ion. Cations have lost 1 or more electrons, anions have gained 1 or more electrons relative to the neutral atom like we see on the periodic table. So for boron, we did this. We know we have 5 protons, 5 electrons then, and it's neutral, so we have 5 electrons. If it were a cation or an anion, we'd have to either remove or add electrons, depending on whether it's a cation or an anion. Next, we want to assign electrons to subshells, starting with the lowest energy subshell, so 1s, then continuing to subshells of higher and higher energy, until we've assigned all of the electrons of this neutral element. For elements in periods 1 to 5, we should fill each subshell before we move on to the next. So remember, these columns are the groups and the horizontal rows are the periods. So these are the periods, those horizontal rows. As we do more examples, we'll see how this fits in. Then we can use the N plus L rules or the periodic table itself to decide the order in which the subshells are filled. Let's start applying these different guidelines to our practice problem we're working through. So a neutral atom of boron would have 5 electrons. We saw that from the periodic table and from the atomic number of boron. So atomic number of boron is 5. It has 5 electrons. It's neutral. So we're not losing any or gaining any, just has 5. Then the lowest energy subshell is the 1s subshell, which can hold 2 electrons. So 1s subshell can hold 2 electrons, so therefore we're already taking care of 2 of the 5 electrons. Then we would go up in energy to assign the next 3 electrons. As a reminder of the order here, so this is on slide 20 of part 1 of 7b. So 1s, 2s, 2p, 3s, 3p. Let's go ahead and make sure we know how many electrons can be found in each one of these orbitals. So in 1s, that is 2 electrons. Right, that's 1 orbital. 2s is still 2 electrons, so number of electrons. 2p, though, that can hold 6 electrons. for the 3 orbitals that are p orbitals, px, py, pz. Then another s here, that's another 2 electrons, 3p, that's another 6 electrons, 4s, 2. What about a d orbital? Well, there are 5 orientations of d orbitals that can hold 10 electrons. Right now in this topic we're just assigning the electron configuration for an element that has s and p electrons only. S orbital can hold 2 electrons, the p orbitals can hold 6 electrons. So then, like we just saw, we're going from 1s to then a 2s orbital. So from that order of energy levels, we know we're going to go from 1s, then next to 2s. After that, we will then start to fill up the 2p subshell if we have any remaining electrons. So we have 5 to use up in 1s that can hold 2 electrons, then we have 3 left. Next up is 2s that can hold 2 electrons, then we have 1 remaining. Then that 1 remaining electron from this neutral atom of boron has to go in the 2p subshell, and there's only 1 remaining, so we see it like this, the exponent of 1. As a reminder for this notation, we originally saw this in 7b part 1 on slide 21. So the exponent tells us the number of electrons in the orbital or subshell. So after we've accounted for all 5 electrons for this neutral atom of boron, fills up 1s, 2 electrons there, 2s, another 2 electrons, 2p, just 1 remaining. That leaves our final answer here for the electron configuration of neutral boron as 1s2, 2s2, 2p1. So we can draw those electron configurations as far as the boxes. We can also write out these electron configurations like this. So 1s2, the number of electrons here in each designated subshell. These are also again listed in order of increasing energy, so lower energy then higher energy. In table 7.3 of your book, it actually gives all the different electron configurations for all the different elements. There are a few exceptions, so there's copper, silver, and gold. So for example, this exception for copper is a pretty common exception to hear about when thinking about elements and their ground state electron configurations. So copper is an exception. Copper is one of our exceptions. It adopts an ns1, n-1 d10 configuration. So for instance, copper is 4s1, so 4 here is for n, 4 minus 1 is 3, so 4s1, 3d10 for copper. Something else I'll point out here for copper specifically, we see argon listed like this, and then we're only showing these 11 electrons actually listed out. So instead of listing all the subshells that come before 4s1 and 3d10, we just denote it with this argon, this noble gas here, because when we show argon here and then copper here, when we put argon like that in brackets, that is saying the electron configuration for argon, then everything else listed right here for copper. So instead of listing all the electrons leading up to argon, we can just say argon, the noble gas. We can do this bracket technique with the noble gases. And remember, the noble gases are in this column here. So when we saw copper, it says argon and then 4s1, 3d10. So everything for argon, then in addition, the 4s1 and 3d10. Can you figure out why this is an exception based on what we see here? So 4s has 1 electron, but 3d has 10 electrons. Why didn't we completely fill up the 4s subshell before adding in the remaining electrons to the 3d subshell? So the order is correct because 4s then 3d10, but again for copper, we have 4s1, 3d10. we filled up the 3D subshell and we left the 4s subshell partially unfilled. That's because this is more stable than having it be 4s2 3d9. For those 11 electrons from copper that go beyond argon, this is less stable. This partially filled d orbital is less stable than a partially filled 4s orbital. So we would expect this to be 4s2 3d9. For copper though, it is 4s1 3d10. We completely fill the d orbital and we only partially fill the s orbital. That is why copper is one of those exceptions. So again, copper here, one of our exceptions, a good one to remember as being an exception. We also have silver and gold that are exceptions as well, and they follow this electron configuration. Chromium as well. So these are our main exceptions that we think of. So copper and chromium definitely, and then silver and gold as well. Let's see why chromium is an exception. So chromium has argon listed here as well because that contains the same number of electrons as argon plus 4s1 3d5. So plus 6 additional electrons relative to argon. So for chromium, this is 4s1 3d5. Again, why did we fill up 4s1, so 1 electron in 4s and 5 in 3d, rather than completely filling 4s? Well, 4s is one orbital that can hold up to 2 electrons. So if we were to fill chromium like we would expect, we would do 1, 2, then there'd be 6 more to account for, so 3, 4, 5, 6. That leaves this one orbital of d empty. This is not very stable, so instead, to make this more stable, instead of having this electron be paired with the other electron in the 4s subshell, we're going to move that electron to fill up this 5th orbital of d. So these 6 electrons dispersed like this, where there's 1 in 4s, then 1, 2, 3, 4, 5 amongst the 3d orbitals, that is more stable. That is why chromium is also an exception. So remember, our exceptions are copper, silver, gold, and chromium. They are exceptions because their electrons don't pair like we'd expect. Instead, they'll have some different configuration that's unexpected. It's an exception, but it leads to an overall more stable electron configuration. Let's try this practice problem. So example 7.12, an oxygen atom has a total of 8 electrons. Write the 4 quantum numbers for each of those 8 electrons in their ground state, so in their non-excited state. Non-excited, or our standard state. So when electrons are in their ground state, it's when they're in their most stable state. It means we're not going to have one electron way up here in this excited state. Instead, every electron we're going to work on that practice problem is in its ground or stable state or lowest energy state. So lowest energy state, let's go back to that practice problem now. So 8 electrons all in their lowest energy state. Lowest energy or expected state. We have 8 electrons to work with. We want to figure out all of the quantum numbers for those 8 electrons. Well, we need to start filling up the subshells with those 8 electrons. Once we figure out those n values, the electrons fill up, we can then figure out the L values. From there, we can figure out the M sub L values. Then we need to keep in mind the Pauli exclusion principle as well as Hund's rule. So we covered those in 7b part 1. They should sound familiar from 7b part 1. Let's figure out where these electrons will exist. We know we need to fill the 1s first. That's going to cover 2 electrons, so 1, 2. Next is going to be our 2s. That can also hold 2 electrons. Notice we pair these before moving up to the next energy level. In order of increasing energy, we have 1s, 2s, then 2p. 2p has 3 orbitals that can each hold 2 electrons. We need to fill 4 more. So we're going to do 1, 2, 3. Then we are forced to pair another one here. So this is paired. These are unpaired. That is 8 electrons total. We needed these energy levels in order, and we need to be familiar with how many electrons an s orbital can hold, as well as p. So s can hold 2 electrons. P, there are 3 orbitals that can each hold 2, so that's up to 6 electrons for p. So now that we have this written out, let's assign the n and the l value, and then the m sub l value and the m sub s. So for 1s, that is n equal to 1, 2s, that is n equal to 2, 2p, that is also n equal to 2, so s, p, d, and f, that is l equal to 0, 1, 2, 3. For s then, l is equal to 0. For s again, l is equal to 0. For p, l is equal to 1. For possible m sub l values here, we know it's going to be negative L through 0 up through positive L. For L equal to 0, the possible m sub l value is just 0. For L equal to 0 again, the possible m sub l value is again 0. Here for 2p, L is equal to 1. M sub L then, there need to be 3 possible m sub L values to match the 3 orbitals of p. So this can be -1, 0, and 1, minus L, 0, through plus L. Now, based on us filling up 2 electrons here, we're going to have ms equal to +1/2 and ms equal to -1/2. Same thing here because we have 2 electrons. Same thing here because we have 2 electrons. Here though, this is just going to be an ms of +1/2, and same for this one. There's only 1 electron here. You could say spin up or spin down for those single unpaired electrons. Again, it's customary to say spin up for just a single electron occupying an orbital. So paired, 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 and then unpaired here. And again, customary, we say these unpaired ones are both spin up. Technically, they could both be spin down. Again, we should get comfortable just saying those unpaired electrons are spin up. So in writing out all the orbitals, all of our quantum numbers for each electron, for the first electron, we know that was n equal to 1, L equal to 0, m sub L to 0. Then we have a +1/2. For the second electron, same thing, but we have it in -1/2. So that now accounted for these 2 electrons we've taken care of now. Next, we were in the 2s orbital, so that was n equal to 2, L equal to 0, ml equal to 0. M sub s could be spin up or spin down, so those are those 2 electrons. That accounts for these 2 electrons here with this information. Now let's go on to 1, 2, 3, 4. We need to assign 4 more where n equals 2, L equals 1. M sub L can either be -1, 0, or 1. So in assigning these orbitals to the different m sub L values, it's essentially arbitrary. We could say this is m sub L equal to 1, m sub L equal to 0, m sub L equal to -1. So m sub L equal to 1 has 2 electrons, 0, just 1. M sub L -1, just 1. We could have put that additional 4th electron in any one of the m sub L slots, technically. So for n equal 2, L equal 1, m sub L equals 1, let's say we have a spin up and a spin down. So n equal 2, L equal 1, m sub L equal 1, we can have both a spin up and a spin down to account for 2 electrons. Then what's left over is just a spin up for m sub L equal -1 and 0 here. So that placement of the 8th electron, like we were just talking about, the placement of this 8th electron could have gone in the m sub L equals 0 or the m sub L equals -1. It was arbitrary. So we labeled m sub L equal 1 here as having spin up and spin down. It would have also been totally fine to assign that other electron to the -1 m sub L or the 0 m sub L. So either way to list that is totally correct. There is another practice problem you can work on. So it's example 7.13, just part A in the main slide deck could be used for additional practice here. Next, let's write the electron configuration of an atom or atomic ion now with s and p electrons only. We know cations have lost one or more electrons to be positively charged. Anions have gained one or more electrons to be negatively charged. So let's write the electron configuration for an aluminum cation with a charge of +3. So let's go up to the periodic table and see where aluminum is at, knowing that it's a cation here with a charge of +3. So for aluminum, let me erase this box for boron. For aluminum, this has an atomic number of 13. So this would have 13 protons and 13 electrons as a neutral atom. In its neutral state, 13 protons, 13 electrons. For this to now be a +3 ion, this is aluminum, just neutral. So for this to be aluminum 3+, what must have happened? It's a cation. It had to lose one or more electrons. If this is +3, it had to lose 3 electrons. It lost some of the negative charge to become a positively charged cation, went from neutral to +3, lost 3 electrons. We are only dealing with 10 electrons here for this practice problem. So now we're going to follow these same steps. We need to count the total number of electrons. We do this very carefully because if we don't end up counting the correct number, then we're not going to have the correct electron configuration. Next, we'll assign electrons to subshells starting with 1s, so 1s, then 2s, then 2p, etc. We would fill this subshell before moving on to this next subshell. We could use this rule of n+1 to decide the order in which the subshells are filled. If we're using that diagram to show the order of increasing energy, then we don't need to use this rule, but this could help check to make sure we have that order listed correctly. For instance, this is n equal to 1. For s, that is L equal to 0. 1 plus 0 is 1. Here, n is equal to 2. L is again equal to 0. So n equal to L equals 0. 2 plus 0 is 2. So this is indeed a higher energy than this one. Let's just do this one real quick. So n equal to p, that means L is equal to 1, right? S, P, D, F, 0, 1, 2, 3 for our values for L. 2 plus 1 is equal to 3. So indeed, we did have this order listed correctly. We could check that with the n plus L rule if we wanted to. For aluminum again, we're filling up 10 electrons just to start figuring out how many different subshells we need. 1s and 2s each hold 2 electrons, 2 electrons. Next is 2p, that holds 6 electrons. Because we only need 10 for this ion, this cation of aluminum, this is actually all we need, right? 1s, 2s, and 2p would cover our 10 electrons. So we only have 10 to work with, again, because it's a cation. A neutral atom of aluminum has 13 electrons, but we've lost 3 electrons for it to be a cation, so we have 10 to work with. In 1s2, that holds 2 electrons. Now we have 8 left. 2s2, that holds 2 electrons. Now we have 6 left. 2p6 can hold those 6 remaining electrons. Because this ends up with a filled subshell of 2p6, this is why aluminum prefers to form 3+ ions. This leads to there being completely filled subshells, which is a really stable form of the atom. Neutral aluminum has 3 additional electrons that would go into the next subshells. When it loses 3 electrons, it's at a perfectly completely filled subshell with all paired electrons, and that is a really stable form of aluminum. That is why, for instance, the halogens gain 1 additional electron, the alkali metals lose 1 electron to become +1 cations, the alkaline earth metals lose 2 electrons to become +2 cations. So these elements will lose and gain electrons to become more stable. The electron configuration, therefore, for aluminum as a 3+ cation is 1s2, 2s2, 2p6. 2 electrons, 2 electrons, 6 electrons, totals up to 10 electrons total. So be careful with the ions. If they've gained or lost electrons, you need to account for that in their electron configurations. Next, let's do counting valence electrons in a neutral atom. So we've talked about valence electrons briefly. Let's go more into valence electrons and use the periodic table to predict the number of valence electrons. So for an example, how many valence electrons are in a neutral atom of silicon? Let's see. For main group elements, so these and these, we generally just think about the number of valence electrons in these 2 groups and in these groups. So for these main group elements that I've highlighted, the number of valence electrons in a neutral atom for one of these elements is determined by the group it belongs to. So for instance, these all have 1 valence electrons, all of our alkali metals. These all have 2 valence electrons, all of our alkaline earth metals. These all have 3 valence electrons, these all have 4 valence electrons, and so on. So 5, 6, 7, and 8 valence electrons. 8 valence electrons is a happy complete octet. Noble gases have a full complete happy octet. That's why noble gases are fairly unreactive. They're not going to react to either gain or lose an electron to become more stable and have a happy complete octet because they already have a happy complete octet. And an octet here means that the outermost shell has 8 total electrons. We'll look more at octets and duets, especially as we're drawing Lewis dot structures and predicting the stability of atoms within bonds. So one atom bonded to another atom, what makes that a stable bond? What makes that a stable compound or molecule? Well, it involves a sharing of electrons to reach a happy complete octet. Again, we'll talk more about that as we get into Lewis dot structures coming up here fairly shortly in the semester. So remember, periods are horizontal here. Our groups are the columns. We were asked about silicon specifically. That is in group 4A or group 14, depending on how you look at these titles here. In group 4A, these all have 4 valence electrons. Oxygen, then, for example, has 6 valence electrons. fluorine, 7 valence electrons, and so on. I do want to point out this exception here for helium. So these all noble gases, these have 8 valence electrons. They are happy in their full octet. Helium actually forms a duet, just like hydrogen. So helium is happy with 2 valence electrons. So helium is happy with 2 valence electrons in its outermost shell. So watch out for this exception where helium has 2 valence electrons even though it's in group 8A. Okay, so really watch out for this example of helium that only has 2 valence electrons, not 8. And we'll come back to talking about hydrogen and helium wanting to form duets. The rest of the elements typically like to form octets. So 8 electrons in the outermost shell, just 2 electrons in the outermost shell to be more stable and happy. Okay, so for our practice problem here, just looking at silicon that has 4 valence electrons in this neutral atom of silicon. It's neutral, it hasn't gained any electrons or lost any electrons to become a cation or anion, it's just neutral. We can see that the number of valence electrons can change if we have an ion. Let's try this ion, for example. So F minus. Generally, F has 7 valence electrons. If we see that minus sign here, that means it's an anion that's gained 1 additional electron. That means F minus has 8 valence electrons, while neutral fluorine just had 7 valence electrons. So watch out for it saying if it's neutral or an ion, because that definitely affects how many electrons that atom has. So speaking of that, let's go into this now in more detail, counting the number of valence electrons in an atomic ion. We looked at F minus, let's look at N3 minus. Do you remember what this is called, by the way? So we looked at fluoride. We changed that ending to IDE compared to fluorine. Now this is nitrogen when it's just neutral. N3 minus is what again? This is called nitride. Right, so it's the anion form of nitrogen. So F minus, F, fluorine, fluoride, nitrogen, nitride. Looking here, just neutral nitrogen is in group 5A. That would have 5 valence electrons. So I'm denoting this, by the way, as VE, so valence and then electrons. If this is a 3 minus anion, that means it has gained 3 additional electrons. So no longer does it have just 5 valence electrons. This is now plus 3. This is 8 valence electrons for the nitride anion. Okay, so we're here for group 5A. We find nitrogen. Again, for neutral nitrogen, that would have valence electrons of 5. So 5 valence electrons. We are not dealing with neutral nitrogen, though, in the problem. We have nitride, the 3 minus anion. Let's talk a little bit more about the number of protons and electrons in nitrogen. So let's go back up to this version of the periodic table. We find nitrogen here has an atomic number of 7. Atomic number of 7 means it would have 7 protons and 7 electrons, again for it being the neutral form. The same number of positive charge as there is negative charge. For nitrogen to have a 3 minus charge, it has to have 3 more electrons. Still has the same number of protons, right? Protons do not change. Protons are the identifying factor of an element. If you change the number of protons, you have a completely different element. So 7 positively charged protons now, but with 3 additional electrons, that nets out to the 3 minus charge we expect for the nitride anion. So that's how we get the 3 minus charge on nitride. It had to gain 3 additional electrons from its neutral atom that had 7 electrons and 7 protons. Nitride now has 7 protons and 10 electrons. Now, really importantly, the total number of electrons is not equal to the number of valence electrons. We define valence electrons as the electrons in the outermost shell. So while we have 10 electrons total for this anion of nitrogen, we only have the 5 valence electrons we started with for neutral nitrogen, then plus 3 additional valence electrons. So 5 valence electrons plus 3 additional valence electrons, that is 8 total valence electrons. So for valence electrons, we have 8 valence electrons for nitride. In total, though, we have 10 electrons. So let me show this as 8 valence electrons specifically. The way I recommend solving problems like this for ions is to not necessarily look at the total number of electrons like we showed here. Instead, stick to looking at this periodic table, finding the baseline number of valence electrons. Even for phosphorus, it has 5 valence electrons. It has a lot more valence electrons. We only care about the valence electrons for this kind of problem, because we're asked specifically about the valence electrons, not the total number of electrons. So for phosphorus, this is 5 valence electrons, although it has a lot more we know. For phosphorus, we worked on that practice problem. So phosphorus we looked at in 7b part 1. Phosphorus we know doesn't just have 5 electrons, its atomic number is 15. So it has 15 protons and 15 total number of electrons. For the number of valence electrons, however, it just has 5 valence electrons. To show you what I mean here, that the valence electrons are the electrons only in the outermost shell, let's look at nitride and see what shells or what orbitals those fill up. So for nitride altogether, it has 10 total electrons. Nitride for the valence electrons is just 3. Let's see how these 10 work out and see why we're saying that there are 8 valence electrons, the number of electrons in the outermost shell. With 10 electrons, we're going to fill up the 1s orbital first. So 1s2, then 2s2, then 2p6. That is 10 electrons now, right? 1, 2, 3, 4, and then plus 6. That's 10 total electrons. Why then do we say we only have 8 valence electrons? Well, the valence electrons are the electrons in the outermost shell. What is a shell again? From 7b part 1, slide 3, a shell is electrons with a certain value of n. Valence electrons are the electrons in the outermost shell, or the highest value for n. Out of all the possible n values, we have 1 and 2. The number of electrons in the outermost shell, or the highest value of n, that's the electrons in the n equal 2. There we have 2 electrons plus 6. That is 6 valence electrons. So here for the valence electrons, we're just looking at the outermost shell. So 8 valence electrons. Here is 2 electrons. Yes, in total there are 10 electrons. For the valence definition, we're just looking at the highest value for n. So that's 8 valence electrons. That is one way to look at it. It is also important to recognize what the meaning of a valence electron is. So again, the number of electrons in the outermost shell, and be sure you're familiar with what a shell is defined as. Shells refer to the principal quantum number of n. That is, again, one way to solve for it. You could also just look and see that nitrogen neutral has 5 valence electrons. Then for N3- or nitride, that's 3 additional valence electrons. 5 plus 3 is 8 valence electrons. So that is the final answer for the number of valence electrons in this anion. If you have any questions at all, let me know. I hope you're all doing well, and I'll talk to you next time for more on Chapter 7.